Greetings, pre-calc students. This is Mrs. D, here to give you a little lesson on how to use properties of logarithms and even the definition of logarithms. So how can these things be useful? Well, we're going to try to solve a couple of equations here, and we're actually going to separate the ones that maybe we're familiar with here on the left and the ones that we're not so familiar with on the right. And let's remember here, first and foremost, the definition of a logarithm, what it really means when we see this base of 4, base of 4, we know that 4 is the base, and 2 here, because logarithms represent exponents, 2 is our exponent, quite easily written here. The result is x plus 7. So there isn't one single answer here. When I simplify this and solve, I find that x equals 9. Neat. There's lots of good reasons why that makes sense. We could substitute back and show that log base 4 of 16, in fact, does equal 2. We could look at it another way as well, and we'll probably do that on the next slide here. Again, using the definition of a logarithm, what it stands for here, the second equation, our base is unknown, but our power, again, is 1/2. So what is the exponent? I can write 1/2. And the result is 6. So some base to the 1/2 power is supposed to equal 6. Recall that a fractional power there, 1/2 power, is the square root of x, which means to me x is 36. We can square both sides of this equation, inverse operation to square rooting. Those problems you've solved types like that before. These two problems on the right, though, are a little bit different. So I'm going to ask you to kind of just think intuitively first here. If I had log of x equals log of 8. Now notice this is base 10. I don't really know the number for log of 8. You probably don't either. It's something less than 1 but bigger than 0. And if I wanted to figure out the unknown value for the other side of this expression, this equation, log of what number will equal log of 8? Well, we're still in base 10 on either side here. I guess the only thing x could be is 8, right? So let's apply that logic there using the same base, kind of like we did with exponential equations. Since we are in base 10 on both sides here, and that's important to note, the only way that these two quantities will be equal or have the same power is if that base is to the same power. Well, then these results have to be the same. And don't get too excited about the simplicity of this problem. We're going to have to think in a moment. I'm going to isolate x to one side of the equation. I'm going to find that 4x is negative 6, which means x is negative 1.5. Now, I'm not going to circle that answer. I'm going to think about it. Negative numbers generally are not a part of the logarithm's domain. That's the parent graph, of course, log of x. So I'm going to consider this number, and before I determine that it's my answer, I'm going to plug it back in. So I will be looking on the right-hand side here at the log of negative 9.5. That's not a real number. Log base of 10, with a base of 10, positive 10, you will never, ever, ever get a result of negative 9.5. Try as you may, no power of 10 will give you negative 9.5. So what we have found here is an extraneous solution. In other words, there is no real solution to this problem. And that means that these two functions never intersect. We'll look at that graphically in a moment. The last problem here looks a lot more complicated than the others. It is a little bit reminiscent of this last problem that we did. If you'd like, you could move one of these logarithms to the other side of the equation. But let's work with it in the form that it's in, and we will start by rewriting. So let's take that thing that we learned about condensing logarithms to write this a little more simply. Because it's a log of a difference, I'm going to condense this to the log of a quotient. It will be the log base 2 of x over 2x minus 1. and it should still equal 0. Now don't do this. People will try to say that this quantity has to be 0. I'm sorry, that would not be true, because log base 2 of this number, this quantity, you can't take the log base 2 of 0. So don't say that that equals 0. Instead, what we're going to have to use is the definition of this logarithm again. The base is 2. The power is 0. Pow, pow. Power. And the result of raising that base to that power is x over 2x minus 1. I know 2 to the 0 is 1, and that should equal x over 2x minus 1. You could use multiplication on both sides of the equation, and that will undo the division, leaving us with 2x minus 1 equal to x. In other words, x would have to equal 1. Now you could check again, make sure you guarantee that you're within the domain restrictions here. So log base 2 of 1, that's a real number. Log base 2 of 2 minus 1, that's another real number. And in fact, they do subtract to 0. Let's now look at that graphically. We'll look at one of these equations graphically. So we have the log of 5x minus 2 problem that we just did equal to log of x minus 8. We found that this had no solution. Let's see why that is here. So I'm going to graph the two sides of the equation separately. I'm considering the parent graph, natural log of x, or log base 10 of x, if you want to think of it that way. The right-hand side here has been shifted to the right 8 units. About there. New vertical asymptote at 8. Rough sketch, okay? The left-hand side has also been shifted, but it's been horizontally shrunk. So I'm going to factor out that 5 to see the exact shift, which is 2/5. And this is a horizontal shrinking factor. So this graph is also shifted a little bit. And there's my x-intercept, let's say, and it's horizontally shrunk. So that's actually going to kind of appear to be elongated. And look at these two functions, these two logarithms. Do they ever intersect? Are they ever equal? No, sir. So that is why we have no solution, found algebraically as well as graphically. For this last problem set, we're going to look at properties of logarithms and how they can be useful to find other values. So at the start here, I'm giving you two values. Log of some unknown value x is 3.4. Log of some other unknown value y is 2. We're going to find the log of x cubed y squared. Now please, 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 please do not think that x is 3.4. You cannot, I repeat, you cannot substitute 3.4 for x. That is the value of log of x, okay? Nor can you use this value of 2 for y. That is the log of y. So let's use some properties of logarithms here to rewrite this. I'm going to first start with the fact that we have a product here. So I'm going to add these two logarithms. And then I'm going to utilize the power property, which gives us the same thing if we look at this as 3 log of x plus 2 log of y. Now I've done this rewriting, and knowing the values that I know, I can now substitute. So the log of x, remember, is 3.4, and the log of y is 2, and so we will have 9, 10.2 plus 4, final result, 14.2. Did we ever find x or y? No, but we found the log of x cubed y squared. Ta-da! Last problem here, we have the log of x over squirty. No, that's x over the square root of y, to the best of my typing abilities. And now let's use another property here. Let's look at this in a simpler way. Wouldn't that be nicer to look at as log of x minus log of the square root of y? I'd say so. I know log of x is 3.4, so I'm halfway there. I do not know the log of the square root of y, though. So this would be an advantageous time to look at that as y to the 1/2 power. So as a power, I'll bring that out in front here as a coefficient. And so I will do 3.4 minus half of log of y. Half of 2 is 1. So 3.4 minus 1 is 2.4. Final answer. Again, we never found x or y, but we were able to find the log of this quotient, x over the square root of y. Just as a summary here, our properties of logarithms are useful not only in simplifying expressions, making things look easier, less complex, more easily understood, but also for evaluating, like we just did with those log of x, log of y values. And equivalence, just in general here, when you have logarithms that are equal to each other, equivalence occurs as long as they're in the same base. Equivalence occurs when you have the same quantity here, the same results, as long as they're the same base. And when you don't have multiple logarithms and you're equal to some constant, just remember the property of, or the definition of the logarithm, that this base has that power c, and the result is always that value that you see here inside the logarithm. Its input is really the result of raising that base to that power. Okay? Do your best, keep thinking, keep problem solving, you can do it.